All right. Hello, everybody, and welcome to the stream. Tonight's stream is going to be a little bit different in that we're going to hit a lot of stuff. So we're going to wind up having to maintain quite a high velocity to get through everything I have planned for tonight. But with all that, how's everybody doing tonight? I hope you guys are doing well. Before we jump into things, I do want to take a quick second and just thank our supporters of the channel here. So that would be our partners, which is the highest tier subscription on Patreon and YouTube, and that would be Arslia, Garboli's Inc., Patrick Kuhlman, and Wen Shang. I'd also like to thank all the other supporters listed here on the screen. Those are people who are subscribed on the other tiers of Patreon and YouTube, as well as here on Twitch. So thank you all very much for your support. It is greatly appreciated. And I would also like to thank each and every other one of you who is just following along and, just here keeping me company and going on this journey with me. I appreciate you guys. Appreciate you, each and every one of you. So thank you guys for being here. All right. So, before I go on, I actually have a new prop, which is kind of cool. It's something the wife got me. Something I might wind up using on stream from time to time. It's like this little Mario cube thing. And if you push down on it, it lights up and makes a noise. And if you turn it off. So I might wind up using that from time to time. I haven't really figured out what, but I might make something on stream redeemable or something. Something along those lines. If you guys have any ideas, let me know. All right, the only other thing I want to bring up before we kind of jump into the stream here is I did just notice that it's storming outside, so hopefully the power doesn't go out or anything like that. Hopefully I don't lose internet, so if I do, it is what it is. But with all that said, let's go ahead and get jumping into this, right? So I have a list of things that I want to go over tonight because we've made quite a lot of changes off camera that I want to go over. And all of this is preparing for the editor. The editor is something I've sort of brought up several times throughout the series as this thing that we're eventually going to get to. And now we're actually going to start making preparations for that. So what I've got here is I actually have this step open in VS Code. And that is because it's just a little bit easier to see the diffs. So, as I mentioned, I've done a lot of work off camera just to sort of get past all the mundane work and stuff that needs to be done. So, there are several things that we have added. One of the first things I'm going to just briefly touch on is something that I added for those of you who are following along in Vim. It's something that I've been meaning to do for quite a long time, and even those of you who are not following along in Vim, it's a little bit of an update to our build system. So what we have is you'll see a bunch of these compile flags. We've got one for each library, and that just contains the imports, or the include paths rather, as well as some defines. And that is for each one of the libraries, so that all of our syntax highlighting shows up correctly and whatnot. Along with that has come a few minor tweaks to our build system. So I got rid of the global compile flags, right? Because some libraries have different includes and requirements than others. So I got rid of that one. And then I modified the build files a little bit. So let me see. Those are in here somewhere. Right here, the make files. So I went ahead and just slightly tweaked some paths in here. Just to make these easily findable and changeable. And so basically what happens now is I use this build file to run a new recipe here called gen compile flags. And so we only have one source of truth as to what all the flags are that are used, whether it's for our code or whether it's for our compilation, and that is these build files, right? And we accomplish this by echoing the include flags and the defines to a compile flags for that specific library that's being built or executable. We run it through a couple of programs here, so we basically just take those as we've defined them here in the file. We replace the spaces between them with new lines just to get them to show up on a new line, which is a requirement of that file. And then we run it through a program called sed, which basically allows us to modify the stream of text as it goes through. And basically what this does is it finds anything with a /i dot / and replaces it with -i, 2 dots, and then a /. And that just allows us to have proper pathing for our compile flags text files. So those are the changes to the build system. Nothing too crazy. There were a couple of changes in the shell scripts for that as well. I should mention I've only done this portion for the shell scripts. The Windows batch files I'll have to update at another point. Okay, so the next thing that I want to briefly talk about is what all of our other changes are sort of going to rely on. So I think probably the best thing to do would be to open up our friend GIMP. So I'm going to go ahead and do that real quick. Let me move this. And I'll just create a new document. And let's just go with white, right? Okay. All right, so up to this point, everything that we have been doing in rendering has all been triangles, right? We've been dealing with triangles for everything that we render up to this point, whether it's the skybox or the terrain or our meshes. And even our text, right? So everything we've done has been dealing with triangles. And so our rendering pipeline has only ever been designed to work with triangles up to this point. When we start talking about an editor, we're going to need a couple of other ways to display things besides just triangles. And we might want to display things such as a line, just an individual line, like a 3D line, but not defined by any sort of geometry in the traditional stance. Or we might want like a vertex, right? Just to display a single vertex. And we don't support either of these things. So right now we're not supporting this or this, right? We only support this guy. And we actually only support one mode of drawing this guy. So right now we basically, we have what we refer to as a list. Apologize for my terrible handwriting here. But it's a triangle list, right? So when we provide the vertex information to our shaders, just as a quick refresher, we say, okay, well, this is one vertex here, one vertex here, one vertex here, and that's our triangle, right? And so the vertex shader goes ahead and takes care of making that triangle. And then we say, okay, well, the next triangle is also going to have a vertex here, and a vertex here, and a vertex here, right? And so it's listed out like this, quite literally in a list, right? So it provides a full triangle for each element that you sort of step through. There is another way of drawing triangles, which is called and I, again, apologize for my terrible handwriting here. I might just switch to the text editor. But we have something called a strip. Right, and what that does is it allows us to draw triangles basically like this. We define one, and then we share these vertices, and then we draw the next triangle, and then we draw the next triangle, like that, right? So it shares vertices in that way. And this is a little bit more efficient. We'll probably wind up eventually switching our terrain to use this. But there are some drawbacks, right? It's a little bit harder to have random holes in your geometry, for example, doing it this way. Not impossible, just a little bit more difficult, right? So you do save a little bit of memory here. It is a little bit more efficient, but we don't support that right now. We also have something called a triangle fan, right? And so a triangle fan basically has one vertex that is sort of in the middle, right? And then you draw a couple of other vertices like this. And the next one, you start from the center, and you create another triangle, right? And another triangle, and it sort of wraps around like this until you get to the end, right? And so a fan would be useful for capping off the end of a cylinder, for example. That's one thing you could use a triangle fan for. So this is probably not something that we're going to use all that much. but it is another method of drawing triangles, right? So we have these three ways of drawing triangles that are available to us from Vulkan. OpenGL supports this, of course, DirectX as well, right? So these are the main ones we're thinking about. So the next one is lines, right? So our lines, I'm actually just going to drop over here, right? And so our lines can also be drawn in a list, right? And so when we think about a line list, it's very similar to a triangle, only it's 2 points at a time. So we have 1 point, 2 points, that forms a line. And then the next thing is another point, another point, that forms a line, right? We also have a strip, right? And the line strip basically works similar to how a triangle strip would work. So the first line has both of its vertices defined like that. You get a line out of it, but then you only have to add another vertex here to the end, and bam, you have another line, right? So it's another form of drawing lines that can save you a little bit on memory if you have something that would use that, right? So we've got that. And there really isn't a fan for lines because that doesn't make sense, right? Triangle fans make sense because of the way that you can lay them out, but you don't have that for lines. The last, but not least, is the points, right? So the individual points. And for points, we only have the list, right? So just as you would expect, you have a point, you have another point, you have another point, right? And it literally draws a point on the screen. And that's all it does, right? So if we have something where we need to grab or edit vertices, that's what you would use to draw the vertex on the screen, right? And so obviously it doesn't make sense to have a strip because a vertex or a point is a single vertex, right? It's not like a line or a triangle that requires multiples of those, right? So all of these are things that we want to support, right? But currently this is the only one that we currently have support for. So what we're going to do is we are going to add support for all of these. And the support for these exists in the graphics pipeline, which we created a long time ago. There is a caveat though. When you create a graphics pipeline, by default, you create it with one of these, what we call topology types, right? And these topology types are generally immutable by default, right? So if you create a pipeline with a triangle list, if you wanted to draw then a triangle strip, you need a different pipeline for that, right? And so later versions of Vulkan allowed us to do what is called dynamic state, where you can actually change the topology that you're drawing with. So if you wanted to go from list to strip, you can actually do that. And that is something that we're going to go ahead and support. However, like with many things in Vulkan, there is a caveat to that as well. So it's not an accident that I laid these out this way, because what we actually have here are what we call topology classes. And this is how they're sort of defined in Vulkan. And they are determined by their type. So the triangles, right, are one class. The lines are another class. And the point is a class, all on its own, right? So, what are these classes? What do they mean? Well, with dynamic state in Vulkan, you can only change dynamically between the topology types in a particular class. So if we create a pipeline, let's say with a triangle list, we can swap that for a particular draw call to strip, and that's perfectly valid. But we could not then change that over to a line strip or a line list or a point list, right? We could only go within this sort of family or class of topology. So we can switch freely between these guys, right? If we create it in list, we can change to strip or fan or any combination thereof, right? If we create it with a line list, we can only switch back and forth between that and strip. And of course, list in general of point list, you can only really use that one. Now, Vulkan does have something additional to that. Additional members of each of these classes, talking about with adjacency, we're not going to support those right now. I don't see a huge need for it, at least not yet, and I don't really want to overcomplicate it. So these are the ones that we're going to support for right now. So I hope all that makes sense so far. Let me just check on chat here. So Potham7787, hey, thank you for doing this series. It has taught me a lot about game engines. Awesome. I'm glad to hear that. That's the whole goal. I'm hoping to, teach people as much as I know anyway. And of course, it's a learning experience for me as well, because there's all kinds of things that I discover along the way too. So it's mutually beneficial that way. But yeah, I'm glad you're finding it useful. Okay. So all this discussion about topology and topology classes and stuff, and what does all this mean? Well, the things that we're going to be adding to our engine tonight are going to be, first off, a series of debug shapes, right? And we're going to start off with just a simple box. But that box is going to be made up of lines, right? So we're just going to have, a box like this in 3D space that we can use to visually section off an area in space, right? Nothing fancy, right? It's just a box. And what we can use that for is, there's actually a lot of things we can use that for. So initially we're going to use this to mark our light positions in 3D space so we can actually see where the lights are. Because right now you can only kind of see where it shines if it happens to be close enough to a surface, right? So we're going to use that for that, at least right now. Eventually we are also going to use this to highlight where the bounding box of an object is. So that way when we actually select an object, we can highlight its bounding box and it makes it a little bit more obvious as to what's selected, right? And so there's all kinds of things that we can use that for. The other feature that we're going to get in tonight is going to be a grid. And so when you're dealing with 3D space, you typically, you have your 3 axes, right? But as you're turning the camera around and whatnot, it gets a little bit weird to tell what direction you're facing, right? And so what we're going to do is we are going to implement a grid that is going to have a red line down the origin of the x-axis. It is going to have a green line down the origin of the y-axis, which remember is up in our engine. And it's going to have a blue line down the z-axis. And then all of the other lines are going to be this sort of grayish color, right? Drixaville, thank you so much for the follow. Appreciate it. And so what we're going to wind up with is something in 3D space that loosely looks like this, right? And this is a terrible drawing of it, but it should give you an idea of what we're going to create, right? So we're going to wind up with something like this. And what it does is it gives us our sort of bearings in the scene, right? Because we can clearly see where the origin is, and we can see where this sort of ground plane is. And so with that, one of the other minor changes I made is I actually moved stuff around in the scene, sort of off camera, to figure out where everything needs to go so that we can clearly see all of that. Apothams, thank you very much for the follow. I appreciate that. And so we are going to put in a grid, which is a pretty major tool when it comes to, analyzing a scene and whatnot. So, all right, let me switch over. I think that has basically covered what we need to go over. So, for some reason, my alert boxes are doubling for some reason. I don't really know why. Twitch, I think, is having some issues with its notifications again. All right, so let me dispense with this. And we'll bring up the S code. And we'll start sort of walking through all of these changes. I'm going to go ahead and exit these consoles, get those out of the way. And as you can see here, we have a lot of changed files. So we're going to walk through these a little bit at a time and sort of build up our feature as we go. And the reason I did this off camera is because a lot of this is stuff that you guys have already kind of seen me do on stream. So there wasn't a whole lot of need for me to sit there and troubleshoot it and make it a huge, long, drawn-out thing, right? So I figure it's probably better, at least in this case, to just kind of show you the end product, as it were. And so actually, before we even jump into the code, I can actually do one better. I'm actually going to run this real quick. Right, and I'll go ahead and load up our scene here. And we can see here what we have going on, right? So this is what we're adding tonight. Okay, so we've got a grid back here. We have boxes where our lights are in 3D space. And they match also the color of that light. You can see this one here that we've actually animated. It not only does it follow it in 3D space, but it also changes color as the light changes color. So that way you can kind of see dynamically what's going on there, right? And eventually we'll probably come up with a shape that's better than a box. Maybe something that is like a sphere or something that matches the fall off. But for now, this is way, way better than nothing. So there's that. And then we also have this grid here, which you can actually see the x-axis here. And I've actually moved this so that its origin is inside the Sponza mesh, right? So we can see here that we have the origin right here within the Sponza mesh. One thing I may do in the future is add that sort of y-axis going up and down, but I thought it was a little bit noisy. It was a little bit too much. So for now, I haven't done that, but I may come back and add that, or maybe make it like an optional property or something. But yeah, this is basically what we're going to be focusing on tonight. Now, the grid and the boxes do take the depth buffer into mind. So as you can see here, it clips into the walls and things like that. It doesn't draw over top of it because I figured that would make it a little bit harder to see exactly where it intersects, right? And so this grid is at 0, 0, 0. So we can see here that our Sponza mesh and our terrain have been placed a little bit below that. Just to kind of allow us to make effective use of our grid. All right, so that is that. The main changes that we're going to need is it's actually having to do with the way that we load shaders, because if you recall, when we load up one of our shaders, we also have to build a Vulkan pipeline under the hood to support that shader, right? And so that is 90% of where the core logic exists. That, and of course, creating the shapes and the grid themselves. So this looks like a lot of code, but I promise it's actually not all that much, right? So the place that we probably ought to start, I'm thinking, is let's go with the shader config. Okay, so we've actually added a new shader, and this shader is super simple. We called it a color 3D shader, and that is because all it has is it does depth test and depth right? And all that it actually does is it has two attributes, one for position, one for color, right? And that's per vertex, right? That's how we get those boxes to change color dynamically, right? We could just change the vertex information. And that means we can also interpolate between colors too if we wanted to do that. And so the pure goal of this shader is to just draw some geometry with just a solid color, right? Because that is something that is useful, right? And so we wanted to keep the attributes light. As you can see here, the uniforms themselves are actually super light as well. So we have two global uniforms, our projection and our view, the standard stuff. And then we also have one local uniform, which is our model matrix. We don't have any instance variables on this. There's not anything needed there, right? So this is actually, I think, the first shader that we've created that's that way. So, Hydrate Redeem. Thank you for that. So this is basically what our shader config looks like. And the new line that you'll see in here is this topology line. And this is what we're going to build in, and this is what most of the logic that we're adding tonight is actually going to revolve around. So what we do here is we define the types of topology that we want this shader to be able to use. Now the default up to this point has been triangle list. So what we've done is we've actually made this backwards compatible, where if this line isn't defined at all, it just defaults to triangle list, right? Because 90% of the time that's what you're going to want. But in this case, we actually have line list first, and then a comma, and then triangle list, right? And so this means that we can use this shader to draw lines, but we can also use it to draw solid geometry, right? So that means that we don't have to have a separate shader, separate pipeline, separate all that stuff just for that, right? This allows us to reuse stuff a little bit more. And I'm actually hoping at some point to be able to condense the number of shaders that we have, at least our built-in shaders. But for now, that's where we're at with this one, okay? So other than that, everything here is similar to what you've already seen. The vertex shader is simple as you would probably expect. This has our position and color. I did put a note in here. So this is a vector 4. I did that for alignment reasons, memory alignment reasons. So the W is ignored, right? We just don't even pay attention to what's past there. In our case, I think we fill it in with 1, which is for the alpha. I think that's what we're doing anyways. In this shader, all we do is we just pass it over, right? So here's our global uniform, right? Our UBO projection view. Here's our push constant for our model. Here is our data transfer object to the fragment shader. And then, of course, we just set the position using the model view and projection, right? Nothing crazy there whatsoever. All right. So the fragment shader is also stupidly simple, right? It has out color as its only output, of course. Its only input is color, and it basically just sets out color to color, and that's it, right? Simple stuff. So the shaders themselves, we don't really need to add anything to support all of that, right? It's actually all pretty self-explanatory, I feel like, right? The bulk of the work is actually going to come in the pipeline. Let's see, I think I already might have that open. So I don't think there weren't any changes to the interface actually. So everything here is already compatible with the work that we've done before. These changes here were just sort of, I think they were just changing the order of these includes. We did add a couple of things. We added some Vulkan utils here, which I'll step into that when we come across it. We also added resource types, Vulkan types. Actually, that might have been here already. Yeah, Vulkan utils was already moved as well. So we've added and moved some stuff around, right? So the next change is when we are doing our pipeline creation, we are updating our dynamic state. This previously used to have line width. I removed that because I don't think we're going to need it, and if we do, I can always add it back. So I changed out line width with primitive topology, right? So this primitive topology allows us to change the topology on the fly as long as it remains in the same class, okay? So down here in our input assembly, this used to be a super simple section, right? Where basically we just set input topology to triangle list. Like this was the only line of code that was here, right? And we've replaced that with a little bit of logic here. And basically we have supported topology types, which I'll get into here in a minute, which basically says what are the supported topology types for this particular pipeline we're creating. And so we basically do a mask check against that for these primitive topology types that we have defined ourselves. So these are our definition, our Kohi definition of the different types that we support. So obviously we have an undefined here. We have triangle list, strip, and fan. We have line list, strip, and line list and strip, and then point list. And then we also have a max here. And you'll notice that these are all to be used as bitwise masks or bit masks, right? So we can OR these together and store them all in a single integer, and be able to determine from that what types we are actually working with, right? Instead of having to set a bunch of them, right? And then all this does here is just shift the value of point list, which is the last entry in this list, by 1, which allows us to actually loop through this structure, right? And you'll see a few places in code where we actually do that. So this is our definition, and then we map this in the back end to Vulkan's definition of these same things, right? Okay. So that mapping essentially is what's happening here. So we take a look at the primitive topology type that we've extracted out from the mask. Here we're just basically grabbing the first one that we find that's been added to that bitwise integer. And we basically say, okay, well, if our type is the point list, then the input assembly is the VK version of that, right? So we just translate that for all these individual types, right? Nothing too crazy here. And that is basically all that's really being done here. There were a couple of small changes that I made here. So we have this VK set debug object name. This was directly calling Vulkan set debug object name, but that is actually not defined for release builds. So this would not actually build in release mode, which was, by the way, something else I fixed here. So part of these changes was also me fixing the release build, okay? So what we've done is we've changed up this file a little bit. This is vulkanutils.h. All of these functions here haven't changed except for the fact they no longer return a Boolean, because that's kind of pointless. And so now they're just return type void, right? And we now are going to use these macros instead, right? Because we created these macros so that if we are in a release build instead of a debug build, right, we use these, which do nothing. It becomes a no-op at that point. And of course, the C file that accompanies this just has the return types here removed, right? So that's really all that was done in that change. That's the Vulkan utils change. So anywhere where you see this VK set debug object name and it's a change here, that's why that change was there, right? And that is just, of course, to provide a name to the object for debugability purposes, right? So the next one is just that again, and then there's another change here towards the bottom, which I guess I just added a new line down here. Not sure why I did that, but that is the changes for the pipeline itself. Now, this does take some data in the pipeline config. Topology types here. So it's a collection of topology types to be supported on the pipeline. That, of course, has to be fed to us by the Vulkan backend. So the Vulkan backend received some changes as well. Again, nothing crazy. Just mainly a few formatting changes, maybe a dozen or so lines of code, maybe a couple dozen, but nothing crazy at all. So the first change we have here is actually bumped up to API 1.3. There are some issues with using this API version. I probably need to revisit this at some point, but I've decided at this point I want to start using 1.3 because the pipeline dynamic state stuff that we're doing was going to be a pain in the butt, and I was going to have to load extra extensions in 1.2. And I just decided I think it's time to cut over to 1.3 and just make it 1.3 going forward. We may make some other changes, some 1.3 specific changes that may simplify things in the future. But for right now, this is the way we're doing it. Okay. So that's just a minor change there. And a little bit further down, we had this VK begin debug label. Again, this was using the non macro version of that, I think. No, what the issue was here was actually I wrapped it in these debug, this debug if def. And that is because if this became a no-op, right, this whole thing got deleted, and then this was considered an unused variable, right? So I had to wrap this whole thing to say only do this if we're in debug. Minor change there. All right, so the next change is we actually added. Okay, I wasn't going to touch on this, but since we scrolled to it, I guess I can go over it. So we have in the back end, in the renderer, we have geometry create, and then a little bit further down, we had geometry destroy, right? But we didn't have any way to actually update geometry. And we would need to update geometry if we had animated positions or we had vertex color changes, which we do now. So we needed a way to actually update that. And so what we have here is a new function. And this function basically takes in the geometry and says where in the buffer do we want to actually start updating? You know, how far in terms of the total vertex count do we actually want to update? And so here is that offset, and then for how many vertices, and then the new vertex data itself. And the cool thing about this is we don't actually have to provide the vertex size anymore because the particular Vulkan geometry data already has that listed, so we don't need it, right? It's literally just a drop these vertices right into place over the old ones, right? And so that is actually all we're doing right here. I did put a note in here to check that the vertex count is not greater than the internal data's vertex count, because we would need a reallocation for that. So if you try to add geometry, it's going to fail, right? And so at some point we'll support that, but that was a little bit out of scope for what I wanted to do. So I chose not to do that for right now. But that would be a simple enough change, right? Basically all we'd have to do is just resize the buffer and re-upload all the data, and then we're good. Okay, so here we calculate the total size of the data that we're going to load. So we just say the vertex count times the vertex element size, which we already know. And then we go ahead and call render buffer load range, right? And this goes exactly like you would expect. It takes the buffer offset plus the offset, and then total size and vertices, right? Checks that for failure and boots out if you fail. I suppose this return is kind of pointless, so let's get rid of that, right? Now, since this render buffer load range actually winds up using a command buffer and queue and all that stuff under the hood, there's no actual way to immediately return, a Boolean here, at least at this level, right? We could, I suppose, check this, right? But I think it's better to just throw an informational message, right? We could, I suppose, change this to a Boolean, but we're not doing that for destroy. I think we are doing that for create. So if we wanted, we could change that up. I chose not to do that at this point. But that is vertex update. Now, there may be a need for us to update the indices as well. And so the indices, we would need a different function for that, right? But for right now, we didn't need it, so I didn't add it. All right, a little bit further down, when we are creating a shader, right, we keep a copy of the topology types that are in that shader config, right? So when we load up a shader, we read that comma separated line there, and we save it to the config topology types. This is what keeps a copy of that value, right? Because we destroy the configuration afterwards. I don't know if I'll walk through the shader loading. That stuff should be pretty obvious by this point. If we have a little time, I'll step through it. But it's just adding a field, just like we've already done, to all of our parsers going forward. So or up to this point, I should say. So it's not really a big deal. All right. So the next thing in here is a kind of a bigger change, right? And so what we actually have is this is the shader destroy. And what we actually have here is multiple pipelines. So what we're doing is for each, you know what, let me swap this back. So for each one of these classes, we are going to create a pipeline, right? So one pipeline for this class, one pipeline for this class, and a pipeline for this class, right? And the way that this is going to work is that'll allow us to say, hey, shader, we want to change the topology type that you're dealing with. And it says, well, okay, if it's in the triangle class, then we can use this pipeline. If it's in the line class, we can use this pipeline, or otherwise use this one. And then we can select in between which actual topology we want to use, right? And so if we've configured to use multiple of these, we'll set them up. If we've not configured that, we won't set them up, right? So we're only going to set up pipelines for topology classes that we actually are configured to use, right? So with that in mind, that is why we have multiple pipelines. So you'll see here that the Vulkan topology class max has been defined. And what that is that's part of this enumeration for Vulkan topology class. Now we have this Vulkan in here because this is specific to Vulkan. I don't recall whether or not GL requires something similar. I don't think it does. So we don't have to define that there, right? And DirectX is probably going to have something different. And so what we have is we have point, line, and triangle set to 0, 1, and 2. And we're also going to wind up using those as array indices, right? We're going to have an array of pipelines. And so we'll say for points, it's index 0, for lines, it's index 1, and for triangles, it's index 2. And now we have something that we can easily access which one we're actually dealing with. So DDE Twitch username, thank you so much for the follow. I appreciate it. Welcome. And so this class max here just allows us, adds 1 to that, just allows us to for loop through it, right? No big deal. Okay, so what we're doing here is we literally just say, for each one of the pipelines that we have available, we say if that pipeline exists at that index, destroy it, right? And so that's all that changes. In Shader Initialize, this is where most of the work is actually done. Most of the changes to support what we've done with pipelines are actually made here. So a little bit further down, we have a bunch of new code followed by some changed code. So the first thing that we do is we create an array of pointers to pipelines. And it's an array of pointers instead of an array of objects because it makes it a lot easier for us to say, hey, does this pipeline exist or does it not exist, right? So we have the internal shader has a array of pointers, right? So it's a double pointer essentially of Vulkan pipelines, right? So we allocate an array of that, right? Times, you know, the topology class max, which is 3 in this case, and we tag that as an array. And then we go through each one of those and we set the individual type on that, and we set it up basically if it needs to be set up. So we take a look at the shader topology types and we say, hey, if that is using the topology type point list, right, then we know that we need that pipeline. So we go ahead and we allocate one. And then we go ahead and set the topology types. In this case, there's only one. So we just set it to primitive topology type point list. We have the next line class here, or the next class, which is lines rather. And we say if our topology types contains the flag for line list or for line strip, then we go ahead and we create that pipeline. In this case, we go ahead and we OR together the two primitive topology types for line list and strip into the supported topology types for that pipeline. Similarly, we do the same thing for the triangle class. So we check list, strip, and fan. And if any of those are set, Then we go ahead and we say, okay, let's allocate one and then set up the supported types for that particular class, right? And so, of course, that's list, strip, and fan, right? Let me get rid of this so we have a little bit more room. All right, so the next bit of this is basically where we loop through our configuration and all this stuff that we just scaffolded to see what needs to be set up. So this is where we use the topology class max, so we can loop through that. And we check to say, hey, is the internal shader pipeline sub I, does that exist? Was it allocated? If not, move on. We don't need to create a pipeline. If it does exist, then that means that we had one of those types flagged, and we do actually need to stand up a pipeline for that. So this is the pre-existing pipeline config logic that existed here before. This is exactly the same as it was before, this whole section that I have highlighted here. The only thing that has changed is we actually set the pipeline config's topology types to the shader topology types, right? So we just store a copy of that in the pipeline config. Here, the only other change that we've made is we go ahead and we create the pipeline at internal shader pipelines sub I. One thing I do want to mention on this is since this used to just be one pipeline object that wasn't a pointer that existed on the shader, we were passing the address of that. We no longer pass the address of that because each one of these is already a pointer to a pipeline. So be careful on that if you're sort of making these changes manually. We no longer use the address of that. It is a pointer already, so don't take the address of a pointer, right? Okay. This k-free config name, that was there before, so that hasn't changed. Pipeline result, this is all the same thing. It's just indented in one, so that's why this shows up as changed. Now, the next thing that we have to do is we have to figure out what the default should be. And you'll note that I have this marked as a to-do because this logic is prone to potential failure. So basically what we do is we loop through the topology classes, and if we have a pipeline for that class, after all of the pipelines have been created, we go ahead and we go through and we figure out what should be our selected primitive topology type, right? And basically that means within a class, do we want to use a list, a strip, or a fan, or list strip, or just list, right? Depending on what class it is. So we check the pipeline's supported topology types. And we say, we basically just do them in a very particular order, right? So these are defined but in an order that is not an accident, right? So triangle list is the most common one. So that is the first one that actually winds up being flagged, and that's the first one that we'll check for, right? Line list is the first one in that family or class of topologies. So it's not an accident that it comes first, right? Because that's the most commonly used one. So if you wind up using one of these alternate types, you're going to have to be very specific about setting the topology type ahead of time, right? But for right now, we don't have to worry about that. This logic basically just picks the very first flag that's turned on, then it runs into, right? And so for each one of those families, it'll just be the list, essentially. Okay. So we do a little bit of sanity checking here to just make sure that we found a pipeline. And if we didn't, we bleat about it and return false, saying that no available topology classes are available. This shouldn't ever technically really happen unless we've got some really invalid configuration, but even then, that should be caught during the loading process. But I wanted to put this here just to make absolutely sure that we're dealing with something here so that we don't get tons of weird Vulkan errors all over the place. That's really hard to troubleshoot. I'm not sure what the change here was. It was probably just formatting. Yep. Okay. So we're almost actually done with the changes here. Most of the rest of the stuff in here was just minor. We do have a small change to our render shader use. So all this did before was bind a pipeline, right? Now it actually has to bind a pipeline at the bound pipeline index, right? So the shader actually keeps track of what what pipeline is currently considered bound. So whenever we bind this pipeline, we also make sure that this bound pipeline index matches that, right? And so we bind that. And then since we set our dynamic state to use the dynamic topology type, right? We have to call vk command set primitive topology every single time before we issue a draw call. If we don't, that's invalid, and we will get an error for it, and it won't draw successfully, right? So now that we've made that change to dynamic state, we have to issue this command every single time, right? Not a big deal, but it is something that we have to do. Okay. So the next thing here is just an update here. Again, to get the pipeline at the bound index, right? The layout there. So most of these updates are just going to be that, right? Because we only had one pipeline and one pipeline layout before. Now we have to get it by the bound index. This change is the same thing, right? We just have to get that index. A little bit further down. Again, this is the same thing. We just have to get that by the index. Again, this is just for the uniform setting, right? And then there's a couple things here towards the bottom. The debug object name, again, we updated that from calling the old method before to just using this macro instead. And this is going to be the same thing here, right? So that is all of the changes in the Vulkan backend. Nothing crazy, like I said. With that, there also, since we've added a new function to the backend, we need a way to pass that in from the front end. So renderer types has an update to add a function pointer for geometry vertex update, right? It's the only change there. That also means that the renderer front end, let's see, the H file has that, right? So we've added a new thing there. We've also added this to the implementation of that as well to pass that through, right? So again, this is stuff you guys have all seen before. There's nothing new here. All right. Let's see. Was there anything else? We can briefly touch the, let's see, shader system. The shader type just has topology types added to it. So we saw that in the back end, that being set up. So that's just that change. I think the shader loader is probably the only other piece of this that we haven't gone over yet. So basically the shader loader doesn't have a whole heck of a lot of changes. Most of what we've changed here is the shader config now has topology types added to it, right, as we just saw. And then we default that to triangle list. Now, this is the default. This is how we get the default if there isn't one actually defined, right? So all this block of code is here is us looking for that topology line, right? So if we find topology, then we go ahead and we create an array and try and split that string, right? The value rather. And if our count is greater than 0, right? Meaning we didn't just say topology equals and then leave it blank, which would be stupid, but we should compensate for that. So if that count is greater than 0, then it goes ahead and wipes out the topology types and parses them instead from this list. So it looks for triangle list, triangle strip, triangle fan, line list, line strip, and point list. If it finds anything else, it will bleat about it saying, hey, I don't know what you're talking about, bud. And then it'll, error that out to the console. It does, however, attempt to move on. So this is an error, but it does not actually, bomb it out at this point. But it does write it to the log so that if you get errors upstream from that, you'll know exactly what's going on. Downstream, not upstream, downstream. Okay, the only other thing here is obviously we have to clean up the string split array, right? So again, you guys have seen this stuff. There's at this point there's nothing too crazy going on right there, right? That's just the loader. Vulkan renderer. There is this is the plugin, so we actually have to assign that function pointer. Don't forget to do that, or otherwise you'll get an error on the front end saying, "Hey, I don't know what geometry vertex update is." So this is just where that connection's made in the plugin. Let's see. We went over Vulkan utils, Vulkan types. I think we've gone over. That's the Vulkan topology class, where we added topology types. Yeah, I think we've already been over all of this stuff. Here is the Vulkan shader, where we have the Vulkan pipeline array, the bound pipeline index, and the current topology. Right. So I think that's actually it for that feature. So that all allows us to have potentially multiple pipelines that we can use to switch back and forth between different geometry types, right? And still be able to use the same shader for that. So now that system is a whole heck of a lot more flexible than it used to be. All right. Math types. Okay, so the next thing we'll do, I guess, is talk about the math types and some of the underlying types that we have to add to get our new geometry up and running, right, for our new objects. So the biggest piece of this, of course, is our color vertex 3D, which matches our vertex layout for our color shader. So again, we just have position where the W is ignored. And then we have color, right? So the shader goes ahead and plugs in a 1 for that. So we just ignore it for now. If we needed any other flag or something like that, we could just plug it into W and use it that way, right? So this is a nice, neat little package for that. Let me see. Resource types. I think we already touched on this too. Yes, we did. Yep. Light system. Okay, so one thing that we are going to need as well, and I'm going to only briefly touch on this because it's something that is going to vary going into the future, right? So directional light and point light now have debug data that could be attached to it, right? And this debug data varies depending on what is actually using the point light and the directional light. So in this case, that's our simple scene, and our simple scene assigns its own type of debug data. So when it reads this debug data, it knows internally what the types are and how to cast it. If and when we get to an ECS type of scene, that set of debug data will be different, but we don't want to have a different object here, or structure for that. So I've made these as void pointers, and then it's up to whatever is using those to understand what to do with those. So right now, point light and directional light are the only things that have that on there. We'll eventually be adding this to like our mesh, our terrain, things like that. But for right now, we're just going to add them to our lights, right? And specifically, the only one that's actually going to matter at this point is point light. And once we get into the scene, we'll address what that is. All right, let me see here. So that's all the Vulkan stuff. Testbed, I think, only had a camera change. Camera position got changed, and where the light 1 position got changed, where it animates to and from, got changed, right? And that's just part of me moving things around. That is also reflected here in the test scene, right? So we moved the Sponza, the Falcon, and the point lights, right? And then we also added a transform to the terrain, because the terrain before was just created at 0, 0, 0, which meant that the generation of the terrain started at that corner and basically went out from there. So what we did is the size of the terrain is roughly, I think it was like 250 units. So we just basically, we moved it to -50, -50, which was going to be half the size of our grid, right? And so that's going to basically align it with a corner of our grid and still allow us to have the grid sort of origin kind of towards the middle of the terrain. Not exactly in the middle of the terrain, but close. Right, so we just moved the terrain for that. All right, now let's get into the shapes. So I think the way I'm going to touch on this first is probably I'm going to go over the box first, and then I'll go over the grid, because the box is a lot simpler. So the box 3D, and I called it box 3D because I called it debug box 3D, right? Because eventually when we do release builds, this probably will wind up getting nixed, I'm thinking. But all this is it's very similar to a mesh. So it has a unique ID, a name, a size of the box, a color of the box, a transform that it uses to move that around the world. And then it has vertex count and vertices. Now this is somewhere where it differs from meshes, because with meshes we sort of load up the config that contains all the vertex information. We upload that to the GPU and then we throw it out. And in this case we keep it because we need to modify it. We might need to dynamically have it change color and things like that, as we have in our demo here, right? And then we are going to use geometry to represent all the vertex and index information, or just vertex information technically, that is uploaded to the GPU. So this uses the same exact geometry system that our terrain uses and our meshes use. It works exactly the same way because we kept it generic enough where it doesn't matter what kind of geometry we upload, as long as we tell the graphics backend what type of data we're dealing with on the way in, it knows how to handle it, right? And so even though we're dealing with lines here, we can still get away with using the same geometry, which is pretty cool, I think. So we don't have to have like a line geometry versus triangle geometry or anything like that, right? Okay. So we have a create, destroy, right? Initialize, load, unload, and update, right? Same application lifecycle type of stuff, right? That our other in-scene elements have. It has a couple of other properties. So it has the ability to set a parent transform. So this will be useful for when we use it as a bounding box for a mesh. If that mesh is moving along the scene, then we can have it follow along with that automatically. We also have the ability to set the color of the box, right? And we're going to be using that. And then we can also set the extents of that box to resize it, right? And so all those are going to be useful. The only one we're really going to use is this middle one, at least in the beginning, right? So the box 3D is actually fairly simple in implementation. You can see here it's not even 200 lines of code. So basically what we're dealing with here is we have a create, which is basically just taking in the size, the parent, and then outputting a box here. So we zero out the vertices and the vertex count. We create a new transform. I have a to-do here on the name because I haven't named it yet. I don't know if we're going to bother with naming on box 3D. I just haven't created it yet. Might make sense to name it. It might not. This is not something we would ever really use, I don't think, in the world. If we wanted to draw something in the world that's like that, there are cleaner ways to do it than just using GPU lines, right? So I could see us potentially maybe doing that, but if we did that, we probably wouldn't use this debug object to do it. So we may not bother with the name. We copy over the size. We get a unique identifier for it, just in case we need to ever pick it. And then here we have the color defaulted to white. We invalidate some of the geometry IDs and generations, things of that nature. And then we go ahead and return true, right? Our destroy, we actually have a to-do here. We need to zero out some stuff, so I should probably go ahead and take care of that. Parent set basically says if we have a box, set the parent transform to be the parent of the transform on the box, right? The color set basically says if the alpha for some reason is set to 0, set it to 1, because I don't see a reason why we should ever have an invisible box. I mean, I suppose we could potentially maybe want that, but for now we have this in here. Maybe we ought to warn. Right, we should, you know what? Because my thought is, if we don't want to draw this, we should probably just not draw it, right? We shouldn't just set the transparency to 0, or the alpha to 0. We should probably just not draw it. Let's see. Let me catch up on chat, because I see there's been some chat there. Tired Beaver, hello. 3K plus lines of Vulkan. Yeah, there's actually more than that. I just started learning OpenGL. Are the performance games from Vulkan significantly better than OpenGL? So I'm going to say in most cases, no. And that is because OpenGL has been pretty well tuned over the years. And you really have to know what you're doing and be looking to squeeze out every bit of performance in order to actually get performance gains out of Vulkan, right? That's not the reason that we're focusing on it here. We're focusing on it here because there's not a lot of content and resources out there. There's some, and that's certainly grown over the last few years. But I've not seen anybody build a full game engine, with Vulkan as a backend. So we're using Vulkan for now. This particular engine is actually designed to have multiple backends. So we are going to be writing an OpenGL backend. We are going to be writing a DirectX backend and probably a Metal backend as well. And so that was another purpose of me writing this engine, was to demonstrate how that would be handled. So I would say performance gains from Vulkan significantly better than OpenGL, not unless you really, really, really know what you're doing. However, Vulkan does seem like it's going to be the way of the future. OpenGL is being deprecated across the board, so the writing I think is kind of on the wall there. What are the benefits of Vulkan over OpenGL? So Vulkan gives you a lot more knobs to tweak, so to speak. You can really tweak exactly how you want your graphics pipelines to work, exactly how you handle your memory, and all of those things, which OpenGL sort of automated a lot of that for you and doesn't always do the most efficient job at it. That being said, you could definitely shoot yourself in the foot very easily with Vulkan. So you have to be careful, right? Is my bot not working? Because that's weird. The Kohi command definitely should have put something there. I wonder if my bot is busted. I'll bet it is. So what that'll give you is it'll basically give you a link to KohiEngine.com. And that is where you can find all the information on Kohi. Links to the YouTube playlist, links to Twitch, of course, to Patreon, and also the repo is there. So the open source repo, it's all open source. So everything I do here is all on GitHub as well. So that's where you can find all the information about that, as well as links to the Discord server. So cool. All right, I am going to get back to this. So So we were talking about the color setting, right? So here we're basically clobbering the alpha if it's set to 0 and we're setting it to 1. We're basically slapping their hand, right? We go ahead and keep a copy of the color. And then we want to make sure that the box's generation is not invalid ID because that means it's not loaded yet, right? We want to check to make sure that we have a valid vertex count and that our vertices array has been set up, right? Because if we go to execute these next couple functions and those things aren't done, it's going to fail. So setting the color is fine. That's used when we go ahead and set up the geometry, but not necessarily the other way around if it's not loaded, right? So update vert color, we just call that on box, right? And since that's stored here, It just looks at that and sets the vertex color. I'll come back to that in a second. Upload the new vertex data. This just calls the same render geometry vertex update that we looked at before. So in this case, we're having an offset of 0, meaning we want to replace the whole thing. We're uploading all of the vertices, right? And then we increase the geometry's generation by 1, right? So every time we do this, we increase that number. We may or may not want to do that for color, but for right now, I'm just doing it to give us a little bit of an indication of what's going on there. Okay. The only thing that I can actually... I just thought of a potential bug, actually. So generation is a U16, which means that it's only going to max out at 65,535, which is invalid ID. So if it actually hits that, it's not going to come into this again, which will mean that none of this stuff ever runs again at that point. So if we get to this point and box geometry generation equals invalid ID U16, we're going to roll that over to 0. Right? Roll this over to 0 so we don't lock ourselves out of updating. Okay. I thought I saw that happen the other day, actually, because I left it running long enough, but I couldn't think of what caused it, and I think that's actually what caused it. So I'll go ahead and safeguard that. All right. So this extents set actually does something very similar. So this recalculates extents. We'll take a look at that in a second. And, of course, calls the update. Again, we just update all the geometry. It also increments generation. So let's go ahead and put the same guard in place, because that's also going to be an issue. All right. So the next thing to look at is initialize. So this is basically where we set up the geometry initially, right? And so we have a vertex count. So we have 12 lines that we need. Each line requires 2 vertices. So we have 2 times 12 here, right? This gets compiled down to a constant, so it's not like it has to run that every time, right? And then we allocate vertices for that, right? We also set up an extents object, and we basically set up the minimum to be negative of the half of the box size on the X, Y, and Z axis. And then the max is positive half of the box size on the X, Y, and Z. And the reason we do that is to generate the box from the middle outward, so that way it's centered. So if you rotate it or anything like that, its origin is in the middle, right? We have recalculate extents. Again, we'll touch on that here in just a second. And then we also update the vert color, right? So if we call update vert color and it wasn't loaded or initialized yet, and then we do initialize it, it's still going to get that color update. Here is the load. So this actually does pretty much what you would expect it to do. It calls render geometry create, passes the size of a vertex 3D, a color vertex 3D rather, and then passes the vertex count and the vertices. However, we do not use indices for this. Why? So an important thing to note is if we think about, I'm just going to bring my image back here. All right. If we think about triangles versus lines, right? If we go to list out a triangle, or draw out. Let's do a new example. Let's do a new example down here. So let's say we're going to draw a quad, right? So we have get white. So we have 4 vertices, right? And then we have triangle A that's drawn this way, and triangle B that's drawn this way, right? So the way that you would set this up to tell the graphics card how to draw this would be you would pass an index of let's say this is 0, 1, and 2. And then to draw the second one, you would pass 0, 2, and 3, right? To tell it what order those vertices are in. That makes a big difference with a triangle because it can determine winding order, which determines back faces and all that stuff. But when you're dealing with a line, you have point 1 and point 2. And it doesn't matter if you draw it this way or you draw it this way. It also doesn't matter because you don't reuse vertices, right? So you're always going to have line 1 is going to be 0 and 1. Line 2 is going to be 2 and 3. Line 3 is going to be 4 and 5, so on, so on, so on. So you're not ever going to have any different order that's ever really going to matter, right? So there's no need to index it at all. And we sort of wrote our shader code with it in mind that we don't necessarily always have to have indices. So everything we've done so far, because it was dealing with triangles, had indices. But for a line, we don't need that. So we don't use it. So that's saving on our overhead and not having to bind an index array and draw that. And it's also saving us on memory, right? Because we don't have to create a bunch of indices that tell us literally 0, 1, 2, 3, 4, 5, right? That's pointless. It just draws them and uses them in the order that they're passed, right? So we were able to save there. And when we go to do points, it's going to be the same thing. We're not going to need indices for that either. So we go ahead and we create that geometry, and then we increment the generation. I don't have to worry about wrapping here, I don't think, because this is on load. And on unload, that geometry gets destroyed and it's invalidated anyways, right? Update doesn't really do anything right now. We could potentially have something that gets updated there eventually, but I don't really see the need. Recalculate extents is, it looks a lot worse than it actually is, right? It literally takes that extent object that we use and uses it to build out the lines that we have, right? And so the way that I've orchestrated this cube is we have the front lines, which are the sort of front four lines that make up the front face of the cube. And then 4 that make up the back face of the cube. And then we have 2 top connecting lines from front to back and 2 bottom connecting lines from front to back, right? For a total of 12 lines or 24 vertices, right? So all we do here is we manually just go through here, and I've set these up so that it uses the min and max extents the way that it should, so that all that works. You guys can review this at length if you want. I'm not going to do that right now because it's all stuff we've seen before, right? Update vert color. All this does is verifies that that the box actually exists, and that we have vertex count and vertices, because if it hasn't been set up, we shouldn't be trying to do it. And then it loops through all of those vertices and sets the color on those vertices to the one that's passed in, or the one that's saved on the box color, right? And that is all there is to Box 3D, right? It is literally that simple to stand up, right? That's all there is to it. It's not a complicated object at all. So that's our debug Box 3D. Our debug grid, by extension, is actually not very complicated either. It's just we generate the lines a little bit differently. That's all it is. So we actually have a debug grid config for this, and that config takes in some properties, right? So we have a name, we have a debug grid orientation. So we have a debug grid orientation of XZ. So that is the sort of default grid that you might think of in an editor that sort of goes along the ground plane, right? And it just lays what you would consider flat on the ground, right? And then we have XY, which is basically it lies on the Z, what you consider the Z plane, right? So it's looking at the default of the camera, right? So you can think about it as it's the default depth, right? Is the axis that sits on. And those are the same 2 axes you would use for a 2D game, right? X and Y, right? And then Y and Z is the plane that's sort of orthogonal to that. So if you were sitting at the default camera rotation and looking, the grid would go off this way, right? Like straight away from the camera, perpendicular to it, right? And those are the 3 axes that we use. And we have that so that we can create different grid orientations for different viewports. Because we're going to have different viewports in our editor. We're going to have one that's for perspective. We'll have one that's for orthographic views and things of that nature. And so we want to be able to just create them on the plane that they're going to be displayed on without having to rotate them, right? So this allows us to do that. So that's the orientation. The tile count and dimensions 0 and 1. So those directly correlate with whatever orientation we have here. So 0 in this case would be X, and then 1 would be Z, or 0 would be X and 1 would be Y, or 0 would be Y and 1 would be Z, right? So we have that. We have tile scale. So this is how large each tile is on both axes, right? So we don't allow non-uniform grids here. And it's relative to a 1 unit default. So what that means is, in our case, we're considering 1 unit to be about a meter in what we would consider real world, right? And so a default tile scale of 1.0 would be 1 box or 1 space in that grid is 1 meter, right? So here is the vertices for that, just similar to what we do for the box. We also have vertex length and vertices for the grid. So that is Vertex 3D as well. And then we also have we have indices here, which actually, did I not take that out? I thought I did. You actually don't need that, because I figured that out after the fact. Let me build this real quick. I think I just forgot to remove that. Yeah. Just to be safe. Do a rebuild. I think it should be fine, though. Because the grid doesn't use it either. So let's get that out of there. All right. In our debug grid create, we take in that configuration. We check to make sure we have that and a pointer to a grid to save out to. We zero out the grid. We set the dimension 0 and 1 to whatever's passed in config. Same with the tile scale. We take a name, a copy of the name rather. We set the orientation. We set the min and max on the 0 to basically the dimension of the grid times the tile scale in the opposite direction. So basically what we're doing is we have a min and max here, similar to what we had with our extents, right? So in this case, if we have a size of 100, right, that is going to be 100 spaces. But what we'll have is we'll basically want 50 on one side and 50 on the other, right? And so what this does is it counts those lengths together on how all those would add up on the opposite, so we know how long to draw each line in one direction of the grid. So we could technically have a 10 by 12 grid or something like that, or a 10 by 100 grid if we wanted to. And all the individual tiles are uniform, but the grid could be rectangular instead of square, right? And so we take the length of the opposite number of tiles times that scale to get how long that line should be in this dimension, right? So we do that in both directions. We start off with extents, meaning 0 extents. We start off with that, and we generate those extents based on what the grid orientation is. So this is going to allow us, like, if we wanted to, for example, create a bounding box using the extents of the grid, and we actually wanted to box off the grid, we can actually do that. So we calculate the extents here based off of the min and max for the X and Y, the X and Z, or the Y and Z. We set the origin to 0. We might eventually want to be able to configure that, but I don't see any reason to for right now. Because it's a grid, it's designed to sort of be centered. It kind of it's kind of a little bit strange to me if it's not. If a grid doesn't start at the origin of the world. We go ahead and we grab a unique ID, and then we calculate our vertex count. So we basically have 2 verts per line, 1 line per tile in each direction, plus 1 in the middle for each direction. So basically what that means is we have 100 lines in one direction, plus an additional one that runs along that axis. Then we have 100 lines in the opposite direction, plus 1 that runs down the center, right? We actually need to zero out and fix our destroy logic for this too. So I have a to-do there. I should fix that eventually. So debug grid initialize obviously just does a sanity check there. It calculates, or it goes ahead and allocates the memory that it needs based on the vertex count that was generated before. Grid line lengths are the amount of spaces in the opposite direction. So here we go ahead and take that again. And then what we do is we actually are getting a index of the elements depending on our orientation. So what that means is if you recall a vector 4, not only does it have x, y, z, but it also has an elements that's an array of floats. And what that allows us to do, is index them by number. And that's super convenient because we can determine what's the first element index and what's the second element index based off of our orientation. And so we can assign a number to those things, and then we can use the same logic all the way down at just different indexes and apply to the elements array wherever we need to be. And so here's the first axis line. And so this one is hard-coded to just be, let's see. Okay, so let me back up for a second. So this not only applies to position, right, but it also applies to RGB. So if I go to, let's see, if I go back here for a second, you'll notice that when we set this up, we have X as the first one, but we also have R, right? And we have Y and G, Z and B, or W and A, right? And so RGBA lines up very nicely such that we can actually use these indices again to determine color. So the first axis that we're going to use, we're going to assign to red, right? So element index 0 on a XZ is going to wind up being the 0th element, which we're going to set to 1.0, which will turn it red. The second axis line is on the Z axis in this case, and it will set that index, which in this case will be index 2, to blue. And so we go ahead and set those two up because they're sort of special in that they're colored. And then we have the alt line color, which is basically the line color that everything else will use. And that is white that is half or semi-transparent, right? And that just sort of seems to be kind of what I've seen in most editors, right? They use a semi-transparent line for grids. Here's where we actually loop through and create lines. So we actually do 4 lines at a time, right? And so the first line, we go ahead and we generate in one direction. And then we do the negative of that line in the same direction. And then we do the opposing third line in the orthogonal direction, and then we do the negative version of that, right? So you can think of this as the max on the X, the min on the X, the max on the Z, and the min on the Z, right? And no matter what orientation we pass here, it will automatically just create it the way it needs to be created, right? So we can reuse the same logic no matter what. And then it goes ahead and sets our geometry's internal ID to invalid ID, just to make sure that we can't actually render it or do anything that we shouldn't be doing before it's loaded. Load, all that does is just pass this off to render geometry create, Again, same geometry system we used everywhere else. Color vertex 3D is the size of our vertices. Have our vertex count, our vertices, and of course we have no indices again, right? So same optimization as before. Unload, of course, just destroys the geometry and sets the unique ID back to invalid ID, and then update does nothing. Okay, so that is the box 3D and the grid. All right. So now that we have that, everything else kind of will just fall into place. The only other places that really had some updates behind them was Simple Scene, which needed a debug grid to be included here because we have it here, right? This is the only thing that we're including here is just the grid, and I may wind up doing this internally instead, but for now, I'm going to leave it as is. And then in Simple Scene itself, we have Simple Scene debug data. So that debug data that I was talking about that gets attached to the lights, that's what this looks like for a Simple Scene, right? In this case, it just has a box. Okay, so any of those void pointers that we have on lights are going to be basically filled with these guys, right? Here we also include our box 3D. And let's see. Add debug data and initialize it. Okay, so we've not done this for directional lights yet. And the reason is because directional lights don't actually use a box. They should be using a line, which we actually haven't created like a line 3D yet. So if we have time, we might create that tonight. I don't know if we're going to get there or not. But this is basically a to-do to initialize that, right? But if we look at point lights, this is where we actually set up that data. So we say the new light that we're creating, dot debug data, which is that void pointer. We allocate some memory for that, the size of scene debug data. Cold cast that to get a convenient pointer to it. Create a box 3D. In this case, we're just making them 0.2, right? We could set that to any size we want. I just figured it's about the right size for it, right? And then we're just storing that in the debug box, right? And incidentally, this 0 here is for this transform parent because lights don't have transforms. They only have positions. We'll come back to that. Well, actually, yes, we'll come back to it right now. If the box fails to create, then we bleat about it. If it doesn't fail to create, then we go ahead and we set a transform position. So we take the box's transform and we set from the new light data position. So we extract the position from that, set that up as a vector 4, and then pass that in here. And we set that so that it lines up with where the light is in 3D space, right? At least when it's initially created. A little bit further down, we have our debug grid initialize. And then we also have our handling of our point light debug boxes. So I have a to-do in here to handle the directional light debug lines when we get to it. So in this case, what we do is we just get a count of point lights in the scene. And for each point light, we go ahead and take a look at its debug data. If it exists, we grab a pointer to it, right? We go ahead and initialize that box. If it fails, we bleat about it. And we go ahead and free the memory at that point, right? We also go ahead and 0 that out and return false. So if initialization of that 3D box fails for any reason, we will actually fail to initialize the scene. Now, I don't think I had any failure code in there, but we put that in place just in case we need to add something later on. So that's that. Here's the debug grid load within Simple Scene load. Pretty straightforward stuff, I think. Here's the point count, the point lights. So again, we loop through the point lights. We grab the debug data. We try to load it. If loading fails, we bleat about it, free it, 0 it out, but we continue on. We don't bomb out at this stage. So if that fails to load, we don't want to completely abort the thing because because a debug shape didn't load, right? So at this point, we just we kind of free it and just silently, move on. Well, not silently because there's an error, but you guys get the point. Simple scene update. So this is a minor thing to update the position of the point lights, right? So we make sure that we're loaded first. And then we have our point light count, so we loop through our point lights. Go ahead and grab the pointer to the debug data. We check the box's geometry generation to make sure that it is actually loaded, which it should be at this point. But we check it anyways, just to be sure. We update the transform, again, taking the box's transform and just taking the light position, which may or may not have been updated by something else. And then we update the color. Now, I do have a note in here that this might be very expensive, and probably is very expensive to be doing this all the time. We might want to think about having maybe another lighter weight version of this, that instead of taking in the color for the entire thing, maybe it just takes in, or I should say, instead of taking in the color per vertex, maybe it takes it in as a uniform and just updates that instead. So that might be a lighter version of this, but I do want to maintain sort of both. So I put a to-do in here talking about that, right? Because this can potentially be a little bit heavy, but again, it's not all that much geometry, and I don't see us having so many of these in the scene that it bogs us down, right? And if we do, we can probably just, snip down the number of them, turn them off, whatever. It's debug only, right? Okay. So this change here was actually a bug I discovered, where this was set to use I as the variable name, and then we had an internal loop that was also using I, so that's very confusing. So thankfully that never caused a bug because of us only ever having one view count. But if we had multiple views, we would have been screwed. So I changed this to be V. Since this is the only thing that uses it, we use packet view sub B. So at the beginning of this, our world data in our scene now has a debug geometries, right? So if we take a look at this, it's just the D array, just like terrain geometries and world geometries. It's the same exact thing. We just have a separate array for that, right? So we go ahead and we clear that. And then down here, after all the other stuff is drawn, we have our debug geometry. So we draw our grid. All we do here is similar to every other type of geometry we draw. We set up a data object. In this case, we have an identity matrix that we use for the model. We have the geometry. We don't have a unique ID for it. I don't think we need one in this case. And then we push it to the debug geometries. I have a to-do here, again, for the directional lights. The point lights, we iterate our point lights, grab our pointer, set up our data. We go ahead and for the model, we call transform world get, which means if there was a parent on that transform that had been updated, this will go ahead and grab that update all the way up the tree, and give us a proper model matrix for that. We grab the geometry and the unique ID off of the box itself because it will have one, and then we push it to the geometries array to be rendered in the view. And that is populating the render packet. When we add a directional light to the scene, if we do that dynamically, we have something here to, first off, release the debug data for replacing the directional light. And then later on to go ahead and add some lines indicating light direction. I just left some example code in here of some of the things that I might do in that case. So we might create our shape, and then if the state is beyond initialized, then we initialize it. If the scene is already loaded, then we go ahead and load it on the fly as well. So the point light add does the exact same thing. So it goes ahead and grabs a pointer to the debug data. I should say allocates and then grabs a pointer. What is 10 plus 1? The third, I think. Welcome. Thank you for the follow, first off. So what is in the debug data for the lights? So the debug data for the lights is just this structure, right? So I've left the debug data up to whatever is actually using the light to determine. So in this case, the simple scene is what is actually using the light. And so it knows internally that we want to represent that light in 3D space in the debug view as a box, right? And so the debug data is basically just this structure with a box. We might add to it, which is why I made a structure. And then, we don't have to change our code all over the place, right? So, okay. So basically, when we add a point light, we come in here, and this is if we're adding it dynamically to the scene. It's somewhere, whether it's been loaded or is currently loading or is already running, what have you. And it goes ahead and creates that light, sets its position, right? And then it says if we're already past the initialization stage for this particular scene, then we go ahead and initialize this on the fly. And then, of course, check for failure, all that stuff. And then if we're also past the loaded stage, right, where the scene is already loaded and we're just adding a new light, then we want to actually load this debug data right then and there on the fly too. So this just handles that. And this is removing a directional light. So if we remove a directional light and we have debug data, we'll remove that. We haven't created the lines yet, so this is still a to-do. And then the same thing for the point light, right? So if we're able to remove the point light, then we go ahead and grab the debug data from that and unload and destroy the debug data there, free the memory, zero it out, right? And then all the way down here at the bottom is just a couple more things. So when we do the simple scene actual unload, this is where we unload the grid. And then this is where we unload, again, the point lights. So again, we just grab a pointer to the debug data, unload it, destroy it, free the memory. And then we actually don't have one for the directional lights. Did I not put a... I did not. So let me actually go ahead and add a to-do in here because that actually needs to be handled here as well. I'm actually just going to copy pasta this. And I'll say... directional light. So if that has debug data, then we'll go ahead and grab that. And then here is where we'll just have to, unload it, right? So to do unload directional light line data. We don't have that yet. So we'll add it. So that'll handle that. Here's where we destroy the array for the debug geometries that we created, right? So that is all there is to the scene. It looks like a lot of code, but it's really actually not all that much, right? It was really somewhat lightweight to actually add all that in. The last component of this is now that we have all this stuff loaded, we have everything set up, it's uploaded to the GPU, our backend is all straightened out and where we need it to be. The last part is actually rendering the stuff, right? And that's actually not going to be as difficult as you might think because of what we've already put in place. So render view world, the render view data now has a D-array for debug geometries as well. So we have world, terrain, and debug geometries for that. And as you might expect, we have some changes in here, but again, not very many. So what we do in the case of this, since we're not using a material system or anything like that to manage the shaders for us, is we are actually going to keep the shader locations within the render view itself. And we're doing that just because it doesn't really make sense to have that stuff outside of this. It doesn't really make sense to have a separate view because this view is also using the world render pass, which is what we use to render all the geometry and what we also need to be within when we render the debug geometry, right? So we can't really create another view. We don't really need to create another view. We can use the same view and then just add this rendering to it. So we save off the locations out of the shader to a structure that looks like this. Our internal data just has a copy of that structure there. And then when we create, we load the color, whoops. That says color 2D, that should be 3D shader. So we load the color shader 3D, which I want to move these built-in shaders to the shader system itself. Right, as far as like the loading of those shaders and stuff, they probably ought to be done there, not here. So this is actually getting the shader resource itself, loading all that stuff up, creating the shader, and then unloading the resource, right? So like this whole thing should probably be done by the shader system. We should probably take all these out of places like this and move them elsewhere. But once we've done that, we get the uniform locations by going ahead and grabbing the shader, making sure that it actually returns something, and then going ahead and getting our uniform indexes for projection, view, and model. Right, those are the only three we need for this. Man, this has come far. Yeah, it has. It has come far. I don't know if you were here when I ran it before, but yeah, you'll. There's some visual updates this time around. Okay, so this is where we build the packet, right? So in this case, we have our debug geometries. Again, we really need to switch this to use a frame allocator so that we're not doing this every frame because this sucks. But our D-array can't do that yet. It does not accept memory that's handed to it from an allocator yet, other than the main allocator that we have for the entire arena. So hopefully I'll have that set up soon. Now that's one thing that keeps kind of coming back that I really need to fix. All right. So when we're building our packet, all we do is we loop through our debug geometries and push these to the out packet, or the packet that we're generating. And we just push those over to the world data debug geometries for the render packet that gets passed off, right? And then we, of course, increment the geometry count on that, right? And the only reason we keep this is so that eventually we're going to keep a counter on the screen so that we can see some stats on how many debug objects we're generating, or that we're, how many debug objects we're rendering versus regular message versus terrain, that kind of thing, right? That's the reason we keep those counters. Here's the destroy, unpacket, destroy. Again, we're doing this every frame. This sucks. I really need to get rid of this, but it hasn't been top priority. All right. So these are where the drawing actually happens for the debug geometries. So the first thing we do here is we see if we have any to draw at all. If we do, we go ahead and grab the shader and we use it. And then we go ahead and set up our globals. So that's our projection and our view matrix. So we set those uniforms. We go ahead and apply those. And then for each geometry, we loop through them. We don't have any instance level uniforms to set. The only thing that we have to set is our model matrix, which is a local matrix, right? So we just set that by index and then we draw it. And that's literally all that's required because we're using all of the other renderer stuff that we set up before. So we literally had to set up nothing new to draw the geometry or to upload any of that geometry to the GPU, even though it's a completely different format, right? Okay, I do believe we have reached the end of the code updates, with the exception of the post-build script where I just added these new things, right? So our color 3D shader, and I added that to the batch file as well, right? So there are some build changes I need to port over to the Windows version of this as well. But for right now, this is what we have. So let me build. What did I foobar? Oh. Yeah, I forgot to update this. This is... should be Durlight. Whoops. Debug data. Why are you bleating? Oh, IntelliSense Ubananus. Oh, I don't even... well, okay. I only don't need that because I'm not doing this down here yet. Okay. There we go. All right. So we'll go ahead and run this. Right. We have our plane scene here, but when we load up, now we have all of our new stuff added. So we've got our light boxes here. So this is just a solid blue light. This is a solid red light. And this is one that changes position and color using sine waves over time, right? And we also have our grid here that was newly added. So if I actually go up a little bit here over our sponza, we can actually see how far out that goes. And we can see that we have our blue line that goes along our z-axis and our red line that goes along our x-axis. And the origin of all of this is in here inside the sponza, right? Again, I think I might add that green line that sort of juts up, but for the purposes of the stream tonight, this is basically as far as I got. I found a pretty neat shader that can render an infinite grid with no geometry. Well, that would be pretty cool. I suppose you could do that, just all shader. This is definitely something that that I want to expand upon, because eventually, the way I want to have this work is basically, I might chunk it, but I might also have it expand out as you move in a direction and sort of hide behind you as you move away, so that the grid sort of creates or moves chunks along with you, so that you're not generating thousands of lines off into infinity, right? Because it only, the grid only reaches here, but our terrain is much larger than that, right? So eventually I'm going to probably extend this to take the camera position into account and I don't know, chunk it or something. Would that be bad for performance? You get a lot of overdraw. You'd be depth testing for every pixel. No. So the way it would basically work is I would just change the geometry on the fly. So then the amount of geometry that's being drawn is always going to be the same. It's just we just update what geometries or the positions within those vertices. It discards all the empty space. Yeah, it's actually very efficient, yeah. All right, so this was pretty much the point I wanted to hit tonight. So I think that's good. We actually got something done on schedule for once, that's neat. We don't quite have enough time to tackle some of the other to-dos that I wanted to tackle. But this is definitely a step in the right direction towards having an editor, right? There's still a few more things that I want in the viewport before we actually physically start building our editor. And those things are, so we already have our selection, or our selectability, sorta, right? So I can hover over the spawns, or I can hover over the terrain, or the car mesh here, and we already get an ID back, right? So we already have all of that working. So we can technically already select objects. We don't have anything that's managing that yet, but object selection is one thing. And then another thing that we need probably to do before we even think about an editor is a gizmo. So that's probably one of the next things that we're going to work on, and those tend to be fairly complicated. And for those of you that don't know what a gizmo is, it's the thing that where you select an object and you basically have the arrows to move it, or you can scale or rotate, and it's an object that you can interact with and do that. So that is probably going to be the next thing that we're going to work on, using this type of hovering object picking, rather. And we're still using pixel perfect object picking, which eventually we need to implement the second form of object picking that's a lot more efficient, which is basically raycasting. So that's another thing that we probably should have in place before we start building out an editor, right? So that we can have some basic raycasting, because that is also going to be needed for like a terrain editor, for example. Cool. Does anybody have any questions before we wrap up for the night? I'll go ahead and take that as a no, but what I am going to do, because I forgot to actually do this last week, is I am going to raid a channel. Let me see who is online that I can raid. Ah, perfect. Pirate Software is online, so I'm going to raid him. So Pirate Software is working on a game called Heartbound, which, incidentally, that's where this soundtrack that's playing in the background is from. He gave me permission to actually use this on stream. So it's a non-traditional RPG that he's been making for a few years now on stream, and it's a really cool project, and he does a lot of really cool things. And I think right now he's still playing Diablo, but yeah, you should definitely check him out and give him a follow for sure. But yeah, I'm going to raid Pirate Software. Normally he doesn't stream at this time, but since he is, I'm going to go ahead and do that. So anyway, thank you guys so much for joining. I really appreciate it. And yeah, we'll see you guys maybe on Saturday. I'm thinking on Saturday I might do a makeup raid, since a makeup stream rather, since I didn't actually stream yesterday because I wasn't able to. So all right, anyway, I'm out. See you guys later.